Hello everybody. Going on with our chapter 15, all about water. This is kind of funny. So read it. Alright, so moving on. We talked about liquid states of water yesterday. Today we're going to talk about the solid states of water. Typically, most solids would sink in their own liquid because they're more dense. As a liquid cools, it begins to contract, and its density, its mass per volume, gradually increases. And because of that density increasing, normally it will sink. But water is a little different, obviously, because of these hydrogen bonds. When we have water in the solid state, ice cubes float on the surface of the water. And this is unusual because not everything else does. And initially, water behaves like a typical liquid. As it cools, it slightly contracts and its density gradually increases until it freezes completely. But when it freezes, solid ice has a lower density than liquid water, and that's because of the structure of it, the molecular structure. It has an open framework with hexagonal air pockets, or space for air to form and be trapped in there. So if you look up here at the top, this would be the structure of solid water, ice, where if you notice those hexagonal spaces are where air bubbles can get caught. And when you have air bubbles in your ice, then it's going to float because it's less dense than the water. So normally we would see if you had iced tea or something, you would see the ice floating. But another picture would be an iceberg where the iceberg is floating on the water, but only a portion of it is above the water that we can see, but we don't know how much bigger it is underneath the water. So when the Titanic sank, they didn't know how much was underneath the water and all that stuff. So moving on, we have what are called solutions when we dissolve things in water. We will talk more about solutions in chapter 16, but water can dissolve things when it comes into contact with it. An aqueous solution is a solution that has water that's dissolving the substances. So whenever you have a solution, whether it be water or something else, the dissolving medium, so what is doing the dissolving, is called the solvent, and the dissolved particles are called the solute. So if you look up the top beaker, we got water up there, where the blue would be the water, and that's the solvent, so what's doing the dissolving, and the solute is the particles that are being broken up or dissolved to make the solution. And we use solutions a lot in chemistry. So substances that dissolve most readily in water include ionic compounds and polar covalent compounds. And that's because of the charges that have to do that with that. So like we saw on the video on Monday, the solution process, what happens is the water molecules bombard the solid, and they break apart into their positive and negative charges, or slightly positive, slightly negatives. And this all has to do with the kinetic energy. So the water molecules will actually collide with the crystal to break it down into its ions, and then the positive ion will get surrounded by the slightly negative charge of the water molecule, and the negative ion will be surrounded by the slightly positive side. Okay, when they get surrounded and they could become completely separated, we call that solvation. So the solution process is called solvation. Here's another picture of where if you would put some salt into water, so this would be the solid form of the salt. If you would put it into the water molecules start bombarding the solid and breaking it apart so that the ions cannot go back together. In some ionic compounds, the attraction is actually stronger than the attraction exerted by the water. And because of this, some compounds can't be solvated, or they can't form a solution, and we call those insoluble. So two examples of this would be calcium carbonate and barium sulfate. If you remember back when we were writing our equations and we had solubility rules, this is what it meant. You couldn't form a solution from it. It stayed a solid because the bonds were so strong that it couldn't be broken apart by the water. What about nonpolar molecules? Well, a nonpolar molecule that does not dissolve well in water you can use different solvents to dissolve it. Some examples of these solvents would be gasoline or turpentine or acetone. Like if you have an oil-based paint, water isn't going to clean off the paint, so you have to use something like turpentine or like a paint stripper or a paint thinner to get the paint off of things that you don't need, like whether it's your skin or something that you accidentally spilled paint on. Another would be acetone, like nail polish. Most older types of nail polish remover contain acetone because that would break up the bonds that were holding the molecules together. So those are just some examples of what can break down a nonpolar molecule. Okay, next, we've probably heard a lot of these on commercials when with food. Electrolytes and non-electrolytes. An electrolyte is a compound that conducts an electric current when it's in its aqueous solution, or in a molten state, meaning it's in a liquid form. A non-electrolyte is a compound that doesn't connect that electric current. All ionic compounds are electrolytes because they dissociate into their ions. They break apart into their positive and negative charge. One of our most obvious forms of this would be Gatorade. Like when you're working out, you need to have those electrolytes to keep you going. That's when we've heard this before in Gatorade commercials. Electrolytes, not only do we drink them in Gatorade, but there are also reasons why we don't use hair dryers or toasters in the bathtub, which I don't know who would be making toast in the bathtub. But pure water, we don't have pure water coming out of a tap. Most often, like around here, there's especially really hard water. Or if you have a water softener, that's putting some salt into your water to break down the hardness of the water, and then therefore it has ionic compounds dissolved in it. So that's why there's some danger labels on your hair dryers and you're not supposed to use it, because since we don't have pure water coming out of our pipes, if you accidentally put an electric charge into your bathtub, then you're going to get electrocuted and the outcome would not be very good. So don't do it, please. Not all electrolytes conduct an electric current at the same degree. So we have strong and weak electrolytes. A strong is a solution that nearly all of the solute is broken apart into its ions, and it conducts electricity very well because of that. So for a picture down here, the left beaker would be a strong electrolyte because it's hydrochloric acid and the hydrogens and the chlorines are all broken apart. And a weak electrolyte conducts an electric current poorly because only a fraction of the solute in the solution exists as ions. So if we look on the right side, not all of this has been broken apart. Like you see here, there's a hydrogen off, and that came from probably from this molecule right here. But all the rest are kind of still together. And because they're still together, it's not going to conduct a current as well as a strong electrolyte. So that's the difference between strong and weak. We do need electrolytes for our metabolic processes, so like breaking down sugars, all that stuff. So that's why you need them, and you need to replenish them after you work out. So that's why Gatorade would be good. But the way that our body uses electrolytes, and most often it's sodium and potassium ions, but it uses it to carry electrical impulses internally to other cells. So if you deplete your electrolytes, then your brain functions and your muscle functions won't be working as well. And so you want to keep having a high volume of electrolytes. I remember back in high school, you go to sports practice, you're at school all day, you eat around, 11:30, noon, depending on what lunch you have, and then you don't really have time after school to eat something. And so you go all the way from noon until getting done with practice at about 6 o'clock-ish, going home, and then you finally get to eat again. I remember when I was in high school, when I first started out as a freshman, that was really affecting me. I would just be so tired, and I would just have a headache, and my body would just be so tired that I would feel like I was going to throw up. And we figured out that it's because my electrolytes were so low. And so I would always have to take a Capri Sun or a Gatorade or something with me so that on my way home I would drink that so that I wouldn't get sick because my electrolytes are so low from basketball practice. And so that's why we need to have those electrolytes in our bodies. So after electrolytes, the next thing we're going to talk about are called hydrates. Hydrates contain water as a part of their crystal structure. Okay, and because of this, it's really cool. They actually have cool colors. So the water contained in a crystal is called the water of hydration. And this is what actually gives a crystal its bright color. So if you look at the picture at the top, the picture on the left, or the compound on the left, is a hydrate, and the one on the right is what we call anhydrous, meaning it doesn't have water in a part of it. But as they're adding water to it, you can see that it's starting to turn the color of the hydrate. So that's pretty cool. A compound that contains water, like I said, is called a hydrate. An example of this, like on the last picture, is called copper 2 sulfate, pentahydrate. To write this as a chemical formula, we use the regular chemical formula, so copper 2 sulfate would be CuSO4. And then we would use a dot to separate the formula from the number of water molecules. And it's not a period, it's up in the middle. And then water molecules, but it would be how many there are. Since it's pentahydrate, that means there's 5 water molecules. So that's why there's 5 H2O. All right? So that might be a bonus question on the test, FYI. So, just so we are aware, the forces holding the water molecules in hydrates are not very strong. So we can actually lose the water, or it can be regained back into the compound. I hope you like that little trick right there. So because of this, we actually do have some common hydrates at home. Epsom salt, I don't know if anybody's ever used Epsom salts before, but that's magnesium sulfate heptahydrate. Okay. Borax, which we used back on Halloween to make our flubbery goop stuff, that is sodium tetraborate decahydrate, so that has 10 waters in it. And then calcium chloride, which we're going to talk about in just, actually tomorrow, we're going to talk about calcium chloride dihydrate tomorrow. That has 2 waters, di. So we're pulling back in our prefixes from our naming chapter, and that tells you how many hydrogen, or how many waters, you have in the compound. I kind of mentioned it before, but any substance that doesn't have water in it is called anhydrous. And the anhydrous form would be the form that doesn't have the vivid color. We've actually kind of done this before, where if you have a hydrate compound, you can actually evaporate the water off from it and change it into anhydrous. So this picture right here would be the copper compound that we talked about earlier, where the blue is the hydrate form, and as you're heating it up, the water molecules are evaporating off. So you can see the condensation up here, and so what's left over at the bottom would be the anhydrous of the compound. Okay, a few more things to talk about today. One is an efflorescent hydrate. When you have water molecules and hydrates that are held by weak forces, they actually have an appreciable vapor pressure because of that, because the vapor of the water will escape into the vapor form to leave the molecule. If a hydrate has a vapor pressure higher than the pressure of the water vapor, the hydrate will lose its water of hydration, or what we call efflorescence. So losing your water of hydration is called to effloresce something. The other side of this is called a hygroscopic hydrate. A hygroscopic, if effloresce means it will lose its water readily, hygroscopic means it will actually take moisture from the air, so take water vapor from the air and absorb it into the compound to make it what's called hygroscopic. Okay, so for example, calcium chloride is very hygroscopic, where it will absorb molecules of water when it's exposed to moist air. And tomorrow we're going to talk about a desiccant, and that's part of it is calcium carbonate sometimes. Or another version would be sodium hydroxide. I had to be so careful with my bottles of sodium hydroxide because they're so hygroscopic that if you let the lid stay off for a while, it's just going to start forming a solution because it grabs so much water from the air to make it do that. Okay, so let's go ahead and we're done for the day. So I will talk to you later.